Good morning, everybody. Welcome to the theory of stellar pulsations. Yesterday, we have started to introduce the strategy which we will follow in describing radially symmetric perturbations and radial symmetric pulsations. So we can restrict ourselves in the following lectures to considering radial pulsation. Everything is spherically symmetric. The background model, the stellar model, of course, is always spherically symmetric. Any other models do not yet exist. So apart from the stationary, from the hydrostatic stellar model, also the perturbations and the following pulsations are spherically symmetric. Well, we have split, or we are going to split our approach into three parts. First of all, or the first step would be we construct a stellar model. This can be done by means either of stellar evolution calculations or by a simple envelope integration, where we can put the star at the observed position in terms of luminosity and effective temperature. We assume a more or less well-known mass, chemical composition is observed, and then we can construct a model which is restricted to the envelope of the star, which excludes the center of the star in which nuclear processes can take place. So this is a nice and easy alternative to do full stellar evolution calculations. Well, the difference between stellar evolution and the pulsations is that for stellar evolution, we assume hydrostatic equilibrium, acceleration is zero, and for the pulsations, we assume the opposite. The pulsations are characterized by deviations from hydrostatic equilibrium. We have a finite acceleration then. Opposite or contrary to the stellar evolution, now the nuclear timescale is ignored because the nuclear processes occur on much longer timescale than the pulsations. The same is partially true for the thermal timescale, and we will see in the following when the thermal timescale has to be taken into account. Somehow the mouse does not work. Can I shift down a bit? Now it's okay. It's again. No. Good. Okay. Okay, that's so. Now the next step in the approach will be that which is motivated by the observations. The pulsations are seen to keep the mean properties of the star the same. So the mean luminosity will remain the same as without pulsations. The mean temperature is the same. The mean radius will be the same. And the pulsations may be regarded as a superposition of variations or oscillations around the equilibrium. Okay, that means we are dealing with small changes. Small means changes of the respective quantities like luminosities around the mean or the stationary value. So these pulsations are small variations of the mean quantities. Pulsations are described as small time-dependent perturbations of the time-independent stationary or hydrostatic stellar model. Okay, so this general strategy, as I already said, will be first of all, at the beginning of a stability analysis, we will construct hydrostatic stellar models, taking either from evolutionary calculations or taking these from an envelope integration. This would be the second possibility. And then we consider small variations around the hydrostatic equilibrium, small time-dependent perturbations around the equilibrium. That means any quantity which now depends both on spatial position in terms of the Lagrangian variable mr. So Q denotes, for instance, luminosity, temperature, pressure, and so on, which depends now both on the radial coordinate. We have spherical symmetry. Instead of the radial coordinate, we may take the Lagrangian mass coordinate and the time. And we split it into two parts, into one part which we assume has already been determined by stellar evolution or by envelope integration, which is time independent. So this is a quantity Q0. This zero means it refers to the hydrostatic stellar model previously or in the beginning determined or calculated by stellar evolution or envelope integration. This is time independent. These quantities do only depend on the radial or the mass coordinate mr, plus a perturbation Q1, which depends then, of course, like the general quantity, both on the spatial coordinate mr and the time t. And what we assume now is that this Q1 is much smaller than, or is smaller than, the hydrostatic or the stationary previously calculated quantity Q0. Small, of course, that needs some specification of small compared to what. Of course, otherwise small is not well defined. Q small means that Q1, the ratio of Q1 over Q0 is much bigger than its square, or that Q1 over Q0 is much smaller than unity. This means small. We compare the hydrostatic model with the perturbation, the hydrostatic model with the pulsation, so to say, and we assume that the ratio of the perturbed quantity of the perturbation relative to the hydrostatic value is smaller than unity. This means that then the square of this ratio is much smaller than its linear value Q1 over Q0. Okay, this is the strategy to follow this, we assume, or it's motivated by the fact that the pulsations are seen to be small compared to the mean values which we observe. So we go with this approach, or with this assumption. We do now go into the equations for mass conservation, for momentum conservation, for energy conservation, and for energy transport. Just to remind you how these equations look like, may I have the switch to the basic physics files? This was the result of one of the previous lecture tests to derive the equations, the physical equations, which govern both the hydrostatic equilibrium and any of the now I have to go very much to the end of this file. Cannot get the, takes a while to get to the end. So, sorry. The radial version of the general equations. Well, you will remember all these equations, I guess. So now we come to the radial symmetry, and we are left at the end. Here we are. These are the equations which we have to solve. The mass conservation equation, then the momentum conservation equation. Without the acceleration term, this would correspond to stellar evolution. Pressure keeps gravity in equilibrium, and this term is zero. Now we switch on this term here. This is new. And then we have the second, the energy equation, dl by the, where is that? The mouse? Okay. Okay, the energy equation, which is describing the nuclear energy production, this may be, the energy production may be ignored. In some cases, we will account for this term even for stellar pulsations. And then we have this term which is related to the thermal time scale. It is taken into account for stellar evolution, of course, and it's also partially taken into account once we consider stellar pulsation. And one of the most important equations is the equation of energy transport here in the diffusion approximation for photon diffusion. And the equation which is considered in stellar evolution is the blue one. This accounts for the change of chemical composition by nuclear reaction. This equation is ignored for stellar pulsations because nuclear reaction take place on a much longer timescale compared to the pulsation timescale. So this is ignored, and we have to consider these four equations: mass conservation, momentum conservation, energy conservation, and energy transport. And we take into account the thermal timescale, this time derivative with respect to the thermal timescale, the time derivative with respect to the mechanical acceleration, and then we will end up with the equations that are govern the radially, the spherically symmetric pulsations. Okay, we assume that our quantities, well, these equations have been solved with respect to zero acceleration. So we can assume that there is a quantity T0, like the Q0, L0, for which this equation has been solved, and we know the solution. And which we know the hydrostatic solution. We can assume that T0 and L0, R0, and so on, P0, are known quantities as a function of the radial coordinate mr. And now we enter this equation with the assumption that Q naught, that some Q, some value for L, is given by the sum of the hydrostatically determined value plus some perturbation, which is now time dependent and spatially dependent. So we entered these equations with saying, for instance, for T, we replace, or let me give an example here. Let's, for example, this is the easiest way here. Let's take this equation here for the hydrostatic equilibrium. So we assume first that this equation has been solved by stellar evolution, for instance, and we have dp0 by dmr is equal to minus gmr over 4 pi r naught to the fourth. So we have the values of p naught and r naught, and they satisfy this equation. These have been determined previously or previous to our pulsation analysis. This term is 0. Now what we do, we say P naught, or P, the pressure is P naught as a function of mr plus P1 time as a function of mr and T. And we insert this into this quantity. So we have that this dp by dmr is replaced by dp naught by dmr plus dp1 by dmr. And we do the same here on the right-hand side. Well, there is this factor 1 over r to the fourth, which is left here. Well, this has to be expanded in terms of a Taylor expansion. 1 over r to the fourth is, so the right-hand side is minus gmr. I will do it here on the blackboard to illustrate the illustrated ones, how this is done in detail. 1 over 4 pi times r0 plus r1 to the power 4 plus, now we have, in addition, we have this acceleration term, which is given by minus 1 over 4 pi. We replace r squared by r0 plus r1 squared, r0 plus r1 squared times the acceleration. This would be here times acceleration. I hope you can see it. The acceleration is d2 by dt squared of r0 plus r1. What is the second time derivative of r0? That's 0 because r0 is a hydrostatic quantity, so we can drop this here. So this is simply a quantity which is only going with r1, with a perturbation. That's because r0 is time independent. What about this quantity 1 over r0 plus r1 squared? And we have these quantities twice, which look similar. 1 over r0 plus r1 to the power minus 4 and the power minus 2. Well, these are done in the following way. So 1 over r0 plus r1, take this to the power 2. We take out of this bracket, we take 1 over r0 squared times 1 plus r1 over r0 to the power 2. Okay? So now we know, we assume that r1 and r1 is small compared to r0. This is our assumption. r0 is a small quantity. That means r0 over r1 is small compared to unity. So we can expand this quantity around the value 1. So this is 1 over r0 squared times what is 1 over 1 plus r0 squared. How does the power series go for this quantity? Pardon? Yes, okay. That's known to everybody. Okay, you're familiar with that. Okay, so I don't need to explain. This is a simple Taylor expansion. It's 1 minus 2 times r1 over r0 plus next term would go with a term which goes with r0 plus r1 plus something. Well, there's a plus coefficient. We don't need to consider it. The next term goes with r1 to r0 squared, and we assume that this r1 over r0 is a small quantity, so we can drop this because it's of second order. Okay, so we have the following relation here. We have well, for 1 over r0 plus r1 to the fourth, we will have the linearized version 1 plus 1 over r0 plus r1 to the power 4 will give a similar result. This is 1 over r0 to the fourth times 1 minus not 2 but minus 4 times r0 r1 over r0 plus terms which we will ignore because they are higher order than the linear term. So what we are left with here is then, what about this quantity here? We have 1 over 4 pi r0 plus r1 squared times the second derivative of a quantity which is already of first order. We have d2 by dt squared of r1 here. So what does it mean for this coefficient? Do we need to consider this r1 here? We don't need to consider it because this is already of first order, so it can only be multiplied with a stationary value. Otherwise, we would have a term of second order in the perturbations. So we drop this here. We can ignore it because this would give a term which is of higher order in the perturbations compared to linear one. And only here we have the -4. This is going to gm over 4 pi r naught to the fourth times 1 minus 4 times this quantity, 4 times the first order perturbation of the radius. So let's do it once again here. So we have, as a result of the perturbation of the mechanical equation, we have on the right hand side we have dp naught by dmr plus on the left hand side we have dp naught by dmr plus dp1 by dmr is equal to minus gm over r to 4 pi r naught to the fourth times 1 minus 4 times r1 over r naught plus or minus 1 over 4 pi r naught squared. We only need to take the unperturbed quantities times d2 r1 by dt squared. Okay, so this is the expansion of the hydrostatic or the mechanical equation. This is the expansion of the hydrostatic equation around the equilibrium, and we're going with the perturbation to first order, neglect all higher order terms which are higher order than linear in the perturbations. Okay, what we observe here is then, well, if we take the first term here, then we have dp naught by dmr for the hydrostatic value, and here we have minus gmr over 4 pi times the radius to the fourth times 1. Well, these two terms, what do they do? This one and this one, the first contributing to the 1 here, they have to cancel because for the quantities with index 0, we have that this have to be, they have to satisfy hydrostatic equilibrium. So dp0 by dm has to be minus gm r over 4 pi r0 to the fourth. So these two cancel. And we are left with a homogeneous linear differential equation for the perturbations here in terms of P1, R1, and here R1 is appearing in the acceleration, and we have kept the time derivative of this perturbation, and we have kept the linearized version of the hydrostatic equilibrium. That's how we linearize this equation, or how we insert our assumption that some quantity is to be split in a hydrostatic value, which we know, and a perturbation value, which is taken into account up to linear order, higher order quantities in terms of the linear or the perturbations are neglected. Is that clear to everybody? I wanted to do it once in an explicit way to let you see how this procedure is performed and how it is done. If there are questions, please ask. Okay. So we go back. This procedure will now be done for all of these equations, and we'll see what the result of this linearization, the process which we are doing now is the linearization of these equations, linearized around some hydrostatic solution which we have determined before in the beginning of the analysis. Can we now go back to the previous file? Okay. This is the strategy, the general strategy for our. Okay. Okay, we neglect terms of high second or higher order in the perturbations, and as a result, the equations become linear with respect to the perturbations Q1. The process which the process which we are doing is called the linearization of our equations. Well, we obtain homogeneous linear equations for our perturbations P1 and R1. Once we multiply such linear equations with an arbitrary factor, what happens? If we have a solution in terms of P1 and R1, if we multiply them by a constant factor, then they will also be a solution of the problem. That means linear equations are always determined, the solutions of linear equations are always determined only up to a constant factor. That means, with respect to the physics, once we have a linear theory for the perturbations, we can superpose any of these solutions and it will give us a solution again. Is that clear to everybody? That means, also on the other hand, that we cannot determine the amplitude of a perturbation, because we can always multiply any solution with an arbitrary factor, then it will become a solution again. That means the amplitude of the solution cannot be determined in principle from a linear theory. Okay, this is a drawback, a major drawback of this linear theory. Keep in mind, you can never determine amplitudes of a perturbation or of the solution of the perturbation equation, because the amplitude is in principle arbitrary. You can always multiply a solution with an arbitrary factor. It will become a solution again. Okay? Amplitudes, keep in mind, amplitudes can never be determined by this approach. Okay, so what shall we do then once we cannot determine amplitudes? Well, this will be the third step of the analysis of the general strategy. Once we found a linearly unstable mode, a mode which, or a perturbation which is unstable according to the linear theory, then we need to do some nonlinear stuff, of course, because only the nonlinearity can be used to determine the amplitudes. So once we have a linearly unstable model, then we have to follow the evolution of such an unstable perturbation into the nonlinear regime once the terms, at least the terms of second order in the perturbations, come into play, and then then determine the amplitude. So the third step, if we have done all that linear stuff, then the third step will be follow the evolution of the instability into the nonlinear regime. This can only be done by numerical simulation. So we have to do numerical simulation, and we have to solve the full set of the equations which we have seen just before. There is no change in the equation. We just take these equations and put them in the computer with an appropriate numerical scheme and numerical code, and then we solve the complete set of equations without restrictions to the amplitudes or without restriction to the magnitude of the perturbation, and then we may derive the amplitudes and the final fate of an unstable model. Well, this is the third step then. We will now, in the following, consider first the linear theory, and finally, at the end of the lecture, we will come to the third step, which consists of following or numerically simulating the evolution of an instability into the nonlinear regime and to determine the final amplitudes of our perturbations. Okay, so the strategy falls into 3 steps. Construct a hydrostatic stellar model, do a linear stability analysis, and the third one, once you have an unstable model, then you follow the evolution of the instability into nonlinear regime and determine amplitudes. And if the instability is very strong, you may not even be able to determine the amplitude, but the star may get disrupted by an instability. So the final fate will not be a nicely pulsating star, but it might be that the star gets disrupted by an instability. Both can happen, but the third step will then be the nonlinear evolution in any case. Okay, questions about that? So the next step we consider is then the linear theory and the linearized version of our equations. Okay, so that's the strategy. Now let's go to the linear radial stability and pulsations. Well, we assume, of course, as said before, we assume a hydrostatic model to be provided by R0 as a function of m, P0 as a function of m, density, temperature, luminosity, and so on, as a function of the radial Lagrangian coordinate being time-independent quantities. Well, our approach is then to assume small perturbations to it. So we say R is R0 as a function of m plus the perturbation R1, depending on mass and time, the same for the pressure and luminosity and temperature and so on. So we insert these into the time-dependent equations. We have seen these before. If necessary, we have to perform a Taylor expansion around the hydrostatic or the stationary values. Let's here do it as an example for the density. That might be more instructive than the linearization I have shown you in detail before. So we write the density in terms of rho naught plus R1, split it into the hydrostatic and the perturbation type. This is in general a function of pressure and temperature. So this is a function of P0 plus P1, T0 plus P1. This is according to a Taylor expansion, the value of the density at P0 and T0. And that is, of course, our rho naught. So the rho naught will cancel. If we compare the left-hand side and the right-hand side, you see the rho naught, of course, cancel. And this will give an expression for the perturbation in density rho 1. So let's perform this Taylor expansion. Then this is the derivative of the density with respect to pressure times the perturbation of the pressure plus the derivative of the density with respect to temperature times the perturbation in the temperature. Now these are already quantities of first order. Of course, we can drop the second order quantities according to our assumption that the perturbations are small. Well, then the coefficients or these derivatives, because this is already of first order, this can be taken at the stationary model or at the zeroth order for the zeroth order quantity. Because if we take here somewhat more than the background or the original value, then this would be of first order. So we would have a second order term. To keep it a first order term, this can be evaluated with the index 0. Clear to everybody? So because this is already a first order quantity, then this needs to be a zeroth order quantity, or it's sufficient to have a zeroth order quantity, plus terms which go with the pressure perturbation and the temperature perturbation squared. Okay, so if we redo this equation, or we reformulate this equation, divided by rho 0, so going to the relative quantities, rho 1 over R0 is then in terms of P1 over P0 and T1 over T0, we go to the relative quantities, relative pressure perturbations, and relative temperature perturbations. Then this is our famous, well-known quantity d log rho by d log p in the stationary, for the stationary value, so with index 0, because this is already a first order. In the same way, this is our coefficient delta taken at the background model or at the stationary model. That means with index 0, because it's clear that we have to have the index 0 here. We drop the index 0 here, and you have to remember that this is referring to the stationary model, these alphas and deltas. So we know these alphas and deltas because they are predetermined by the hydrostatic stellar model. Similar for the 1 over r squared. I have shown you this explicitly on the blackboard, how it works. So this 1 over r squared is linearized in this way. So now we go into the equations. Neglect the quadratic and higher order terms in the perturbations, and you make use of the hydrostatic equation. I have shown this explicitly here because here the stationary pressure gradient cancels the gravity on the right hand side here. That's what is meant with making use of the hydrostatic equations for the Q knots. Okay. Well, let's continue. What do we end up with? Okay, first of all, mass conservation. We are left on the left-hand side with the derivative of the perturbation of the radius. Its dependent quantity is given by minus 2 times perturbation of radius divided by 1 over 4 pi rho r cubed. Well, this comes from the linearization of 1 over r squared. We have dr by dm is 1 over 4 pi rho r squared. This is the linearization of the 1 over rho squared, 1 over r squared term. And this here is the linearization of 1 over the density. Once you linearize 1 over density and express it in terms of the pressure and temperature variation, then you get this term which goes with alpha times pressure perturbation, like the linearization of density you have seen before. Alpha times P1 over P0 minus delta times the relative temperature perturbation. So this is again a homogeneous linear equation with concerning linear equations for the perturbed quantities where the coefficients do depend on the background model or on the hydrostatic model. So you have here the alphas, the deltas, the rho zeros, and the r zeros. They refer to the background model. Of course, the rho zero depends on mr as well. So they are spatially dependent quantities. They are time independent but spatially dependent quantities as coefficients for our perturbations. The equations are linear in the perturbations. Well, I have explicitly shown you how to derive the momentum, the linear momentum equation. That's this here. We have this 4 dp by dm by dp by dm. This is the 1 over r to the 4th linearization, and this here is the acceleration term, where the acceleration is a first order quantity itself because r0 is not time dependent, and then this can be taken as a quantity in the hydrostatic model. So we have to take only 1 over 4 pi r0 squared here. Shown this explicitly on the blackboard, so I don't need to comment on this anymore. Well, there is a +4, and the +4 comes from here. The minus and the minus cancel, so this is +4. Okay, energy conservation will be the next equation which needs to be linearized. Okay, this is energy equation. So in that case, we have to linearize both the gradient of the luminosity. You recover you recover the original equations here, and you have, because the derivatives are again a first order quantities, you have to take the derivative of the entropy, which is behind these time derivatives, with coefficients which do only depend on the stationary, on the hydrostatic model. So this gives minus Cp at the hydrostatic model, the specific heat in the hydrostatic model, times the time derivative of the temperature perturbation plus delta naught over rho naught, quantities in the hydrostatic model, times dp1 by dt. And once you linearize the energy generation rate, if you want to take it into account, then this is given by the energy generation in the hydrostatic model times some coefficient which corresponds to the logarithmic derivative of the energy generation with respect to pressure, or with the logarithmic derivative of the energy generation with respect to temperature, which have to be multiplied with the relative perturbations of pressure and temperature here. Well, this is simply linearization, which is done very well, or in the same way as it's done for the density. And we have, for the density, to remind you, for the density, we have, so epsilon, and later on also the opacity, epsilon and the opacity. Epsilon is a function of pressure and temperature, and the opacity is also a function of pressure and temperature. So what we get here, we simply have to replace the derivative of the density with respect to pressure and temperature by the derivative of either the energy generation rate or the opacity with respect to pressure and temperature. And we get very similar relation. So we get something like kappa 1 or epsilon 1 over rho 0 will be the logarithmic derivative of the energy generation rate or the opacity times the pressure perturbation plus the derivative of the energy generation rate or the opacity instead of the density. Otherwise, it looks very similar to this linearization of the equation of state. So it is done very much the same way as the density is linearized using the formal prescription of an equation of state, rho as a function of pressure and temperature. So it can be done very much the same way for the energy generation rate and the opacity kappa. And we are left then with logarithmic derivatives of these quantities with respect to pressure and temperature. They are denoted by epsilon p or epsilon t, epsilon sub p, epsilon sub t, or kappa sub p, kappa sub rho. That's how these logarithmic derivatives of opacity and energy generation enter the equations. Where is okay? So these are these logarithmic derivatives, epsilon p and epsilon t. They have, of course, to be taken from the stationary model because p1 and t1 are already first order quantities. So if you want to consider the epsilon terms, then they have to be taken into account in this way. Well, energy transport, that's the most complicated version of this equation. Well, we have on the left-hand side, we have to linearize the temperature gradient. On the right-hand side, we have one term. This is essentially the diffusion coefficient. And if I may remind you how the diffusion coefficient or the terms on the right-hand side of the energy transport equation look like, well, this is dl by dmr is something like minus. There is an L here, and there is a 1 over t cubed there. There is a 1 over kappa here. There is, what else is left? There is a 1 over r to the fourth left here. We need to linearize this term. This gives, in terms of the linearization of the luminosity, will give a term proportional to L1 over R0. This is that one. Then we have 1 over R to the fourth. This gives a minus 4 times the perturbation of the radius. And then we have the opacity. Well, the opacity then gives you some of these logarithmic derivatives, like the density which we saw before. This is kappa p. This is the logarithmic derivative of opacity with respect to pressure times the pressure perturbation, and an additional term or a comparable analog term with respect to the temperature. So this gives the derivative of kappa with respect to temperature times the temperature perturbation. So these are the linearized version of luminosity, temperature cubed. Temperature cubed is this factor of 3 here. So this gives a factor of minus 3 times the temperature perturbation kappa, and this is the radius. So these are the linearization of all the terms on the right hand side. Okay, and for simplicity, we have taken out of this bracket, we have taken out some of the quantities referring to the hydrostatic model, which is essentially the pressure gradient, temperature and pressure, and the nabla zero, which is the nabla, the d log t by d log p for the stellar model, for the hydrostatic model we have determined. So this is d log t0 of d log p naught. We keep in mind it's not the radiative nabla, it's not the adiabatic nabla, it's the nabla, value of nabla for our specific model we have determined previous to the stability analysis. Okay, here the definition of kappa p0. All these quantities have to be taken or to be applied in the hydrostatic models because they are multiplied with terms of first order. So these are the definitions of nabla zero and the kappa p's and the kappa t's. Well, there's one issue here, one point I should mention. Well, this is now, if this term would be absent, if this would be unity, then this would be the linearized form of the diffusion equation for energy transport by diffusion of photons. Now we have the situation that in our star we also have convection. And I told you there is an engineering prescription once you try to consider or try to calculate convection for hydrostatic stellar models. This is a mixing length theory, but we don't really know what to do when convection is present in a time-dependent environment. So if there is convection in our star and we are considering pulsations, then we somehow have to treat or to deal with the convection, and actually there is no real theory and no real satisfying approach for that. One of the approaches which is nevertheless used is the so-called frozen in approximation. Well, what is the frozen in convection? This approximation assumes that the convective flux is constant during a pulsation period. So the convective flux does not react on the pulsation. What could be a justification for this assumption? Frozen in approximation means the convective flux is constant during one pulsation period, or is constant on the time scale of the pulsation. What would be how could you justify this approximation? Some idea? Well, if one considers the time scale of convection and the time scale of pulsation, if the pulsation is much faster than the convection, then we might assume, or it seems plausible, reasonable, to assume that the convection will not have time to react, so the convective flux will be maintained during a pulsation period. That's actually the justification of this frozen-in approximation. So we have to ensure that once we take this frozen-in approximation, that the pulsation is much faster than the convection. What about modes which have the same time scale as convection? We'll see later on that there are modes. In particular, those slow modes, which are typically the G modes, they have periods comparable to convection. It's highly doubtful how to treat them. You can assume, or you can justify with plausible arguments, that for fast pulsations like P modes, we will find out later, for P modes and for fast oscillators, the convective flux doesn't have time to react, and the convective flux is maintained during a pulsation cycle. That means the convective flux is constant, or the perturbation of the convective flux is zero. And once you apply this frozen-in approximation, you can do it explicitly, then you will get another factor of order unit here in front of the luminosity perturbation, because you don't perturb the entire luminosity, but only the fraction of the luminosity which is transported by radiative diffusion, and you ignore the fraction of luminosity that is transported by convection. And in that case, you get the ratio of the total luminosity, that's including both the radiative diffusive luminosity plus the convective luminosity. This is the total luminosity and the fraction of the luminosity which is transported by radiative diffusion. This is called the radiative luminosity in the stationary model. In the stationary model, you determine both the total luminosity, the radiative luminosity, and the convective luminosity. Convective plus radiative gives the total luminosity. So you have to multiply this with a factor of the ratio comparable to the ratio of the total luminosity and the fraction of the radiative luminosity. This is the result of a consideration of the frozen-in approximation, which tells you, or which assumes, that the convective flux is constant during pulsation, or the perturbation of the convective flux is zero. Okay, so this is an additional factor which can be taken into account once we have a convective zone in our star. Usually you would not like to consider stars which have big amount of convection. You look usually how big is the fraction in the convection zone which is transported by convection, and you will limit your consideration of models to stellar models which have convection zone where not more than 50%. I would say this is also already very much, where at least in a section of the star, only a fraction of less than 50% is transported by convection. So if convection anyway contributes only, say, 10 or 20%, and you assume, or you take into account convection by frozen-in approximation, you will not make a big error in your computations. But convection, again, I have to tell you, it's a big problem in stellar pulsation and in stellar evolution. And there are some more or less plausible assumptions to treat convection in the framework of both stellar evolution and in stellar pulsation theory. Okay, so that's this is the result of the linearization of our equations. We have done stellar evolution, or determined or constructed a background model, a stationary, hydrostatic, stationary, time-independent model. And these are the equations which describe small deviations from this hydrostatic equilibrium, which are to first order linear equations, and we now try to solve these linear equations. Well, we cannot hope that there are analytical solutions to that equation, so we have to solve the system of the equations numerically. I think I have to stop here. Okay, we have a break.